Okay, after the last class, some people came to me and asked some questions, and I want that to be shared on camera. So, ask the questions now.
Some of the windows are wider and some of the windows are narrower.
Okay, for example, if you look at the computer screen, you might notice that this window is larger, this window is narrower, this window is narrower, and as I showed you yesterday, if you zoom any part of it, you will still see further windows. Now, out of these, some are wider, some are narrower. In general, the thumb rule is that the lower the periodicity, starting periodicity of a window, the wider will be the width of the window. That means, this one, this particular wide window is starting at a periodicity 3, and then it is going through a period doubling cascade through the periodicities of 6, 12, 24 and so on and so forth. While here it is another window, if you zoom you will be able to see this window is period 5, it is higher periodicity, starting periodicity is higher, and so it has a smaller width. Now, why are these bigger or smaller? If I want to explain it, it will require some bit of calculation which are not necessary at the moment, it will only complicate matters, but it is because of that. Remember that inside the chaotic orbits, when it goes to chaos, there are all those periodicities embedded in it. So, if I go back to the original one, yeah, it is here. So, when it goes to chaotic orbit here, can you see the cursor? Yes. It is, if it is somewhere here, then the period 1 orbit has given rise to the period 2 orbit, but this fellow is still there. If you want to see the existence of the unstable orbits, then you can see that. So, here the red one is the unstable orbit that continued to exist. At this point, the stable period 2 orbit became unstable and gave rise to a stable period 4 orbit, but the unstable period 2 orbit still kept on existing, right. So, they go on continuing all through. Now, naturally, when we talk about this part here, there are all those unstable periodic orbits inside the chaotic attractor, right. And then at this point, the period 3 fellow comes into existence, and that goes into chaos through the 6, 12 and so on and so forth. So, all those unstable periodic orbits will be existing after this, so on and so forth. Here essentially his question concerned whether why is this wider. The answer is grossly that this is the largest window, because this is starting at a periodicity 3, which is the minimum available within the chaotic region. In fact, there exists a theorem that says that if you ever observe a period 3 orbit, that means it is inside a chaotic orbit, it is inside a chaotic range of parameters. The famous paper by Lee and York that proved this was titled period 3 implies chaos. So, period 3 is always inside the chaotic range of parameter values, but before that period 1, period 2 are outside. Any other question?
Actually, yesterday we took the function a minus x n square.
Yes, I took a minus x n square.
So, any other function still at third order, fourth order theory of the polynomial, there is still the nature of the curve will be same.
A minus x n square we had taken, and we had
like we obtain this curve like period 1 bifurcating into period 2.
no, we had obtained first with this a behavior something like this, that changed, that changed. Okay. So, we had illustrated the occurrence of what is known as the saddle node bifurcation or the tangent bifurcation with this, which gives rise to the starting or the birth of 2 fixed points at these two points. Now, after this, as you change the parameter a further, it goes up and up and up. You can easily see that all that we have learned for the logistic map should also be here, because here is the fixed point whose slope at some point of time will become -1. This will give rise to period doubling, and then if you have convinced yourself that the period doubling's nature is the same irrespective of the type of the map, so long as it is a smooth one humped map, it will also give rise to period 2 to period 4 to period 8 to period 16 and so on and so forth. Okay. So, this will also lead to the same behaviors. Why did I take this one not the other one? Because this one illustrates the saddle node bifurcation better. That is why, no other reason, just to illustrate. Any other question? There was one question regarding whether there can be a trifurcation. Somebody asked, I forgot who. No, bifurcation is a word, is an English word that existed prior to discovery of these things. Okay. So, that has a particular meaning, particular connotation. When it came to scientific usage, that also brought with it a specific connotation, which is that any change in the asymptotically stable behavior of the system is called a bifurcation, even if it is something like this. So, if it is something like this, you would not call it trifurcation, you would call it a bifurcation from a period 1 to period 3 orbit. But can it happen? Well, it normally does not happen. Normally does not happen if the map has certain property. For example, if it is a smooth map, smooth means everywhere differentiable. If the map is everywhere differentiable, such a thing cannot happen. But if the map is non-smooth, if it is not everywhere differentiable, we can show that it is possible to have this kind of behavior. I will illustrate when and how. There was another question. Okay, you are asking some question. Yes.
Sir, if the eigenvalues are purely imaginary near the equilibrium point, we know there will be loops. But how can
No. Purely imaginary eigenvalues cannot happen in one dimensional maps.
No, sir. It's from the earlier.
Wait. Here we are talking about maps. Are you talking about differential equations? Differential equations.
Yes.
Okay. Yes.
And the orbit.
Yes.
But
So.
how can we say that they are circular? I mean, they can be ellipses also.
Oh yes. Oh yes. We can just say. His question is, when we were considering differential equations and we were considering linearization of the differential equation at an equilibrium point, and suppose we have obtained the eigenvalues and found the eigenvalues to be purely imaginary, then what do we say the behavior would be? Would be something like this. His question is, how do you know there will be circles? There could be ellipses. Well, what is this axis? What is that axis? Are they in the same scale? No, they are not, because one is a position and the other is a velocity or momentum. So, the units are entirely different. So, there is no reason to believe that they will really be circles. Okay. So, all you can say is that the behavior will be topologically equivalent to circles. By changing the coordinates, you can make them circles. Okay. Any other question? No. There was another question, if I remember, which is more or less illustrated by what you see on the screen now, that when it goes into chaos, essentially it has a huge number of periodic windows inside. We can visually see the period window of period starting with period 3, period 5, and here is period 6. But if you look closer, if you zoom any part of this bifurcation diagram, zoom, that means you expand it with a smaller range of the parameter. For example, I can show you a bit of it. For example, let me show you the part that looks like chaos. See, there are more windows. The part that we could not resolve in a periodic window, there are still periodic windows. Okay. Here you can see it is period 1, 2, 3, 4, 5, 6, 7, 8. is period 8 window, something that starts with period 8 and then goes through the double periodicities and so on. So, inside there are infinite number of such periodic orbits. In fact, there are theorems that show that take any range of the parameter, you will find that in the neighborhood of that there would be some periodic window, maybe very high periodic window, all right, but nevertheless there will be. So, if you are inside, if you are sitting in the parameter space at a parameter value for which the behavior is chaotic, look this way or that, you will find periodic windows. Okay. Okay, let us get back now. Fine. Now, you see, when we ended the lecture yesterday, we were talking about this window. Okay. So, let us expand it, and look at it carefully. Here is a period 3 window. At this stage, I do not want to see this. Okay. I do not want to see the unstable periodic orbits. Fine. Now, let us look at this particular transition somewhat carefully. What is happening here? You have understood one thing, that at this specific parameter value, what happens? There is a saddle node bifurcation occurring in the third iterate of the map. That means, if we take x n plus 3 as a function of x n and plot the graph of the map, then we will find that that graph is undergoing a tangent bifurcation, resulting in the creation of these 3 stable points. Fine. What is just to the left of that? Say we are here, take a parameter value somewhere there and let us see what happens, something like this, which is not periodic, which is reasonably chaotic, but you would notice that it is coming again and again to a behavior, say look at this, to a behavior somewhat close to a periodic behavior, okay, somewhat close to a periodic behavior. And in fact, if you take values closer, then you see the amount of periodic behavior is increasing. As you come close to this point, you will find the periodic behavior, range of periodic behavior is increasing, as if, but it will not stay, not that it will stay in this behavior, as if there is a somewhat intermittent bursts of periodic windows, periodic behavior in the middle of chaotic behavior. The question is, how does that happen? In fact, in many experimental situations, you will find that the behavior is more or less chaotic. You can see that it is chaotic, but suddenly when you capture the waveform on the CRO screen, you find that it is a periodic behavior. What happened? It is just that for that small span of time for which you did the grabbing of the waveform, at that point of time it was a periodic burst. Now, how does that periodic burst happen? In fact, this phenomenon is called intermittency. This phenomenon is called intermittency. Intermittency is intermittent bursts of periodic behavior in the middle of overall chaotic behavior. So, we are off to try to understand how does that happen, and we have already seen that as the parameter approaches the value at which the period 3 orbit comes into existence. Look at the behavior, say I will let it run. See, it is running chaotically, but notice what is happening here there is an orbit that is visited more often, and if it is visited, it more or less stays there for some time. That is why you see a darker line here. Can you see that? Okay. So, in order to understand why this happens, let us draw the period 3 window, period 3 composition. See? Okay. Notice what is happening. These chunks of the graph are coming very close to the 45-degree line. Okay. Here also it is coming very close to the 45-degree line, and as the period 3 comes into existence, what happens? It crosses the 45-degree line. Okay. As it crosses, you have this kind of a behavior, and therefore, that results in the creation of this as the additional fixed point. But let us consider the situation when it has not gone into that state. When the behavior is, if you expand that part, it will be something like this, very close, but nevertheless not quite touching. Okay. And suppose we start from an initial condition somewhere here. So, we go to the graph of the map and we go to the 45-degree line, and then what? Then if you keep on iterating it, I will do it in another color so that you can see it clearly. It will go like this, right? It will go like this, which means that this narrow passage between the 45-degree line and the graph of the map, it will take enormous time to cross that narrow passage. It is like a bottleneck. For a long time, it will get stuck there, trying to cross. It will move in that direction, all right, but it will take a long time to cross, and after some time it will cross like this, and then it will go away. So long as it is here, if you look at it, its behavior will be periodic. Its behavior will be like a periodic burst, and then it will again run around, and finally, if it is injected somewhere here, again it will go into that periodic window. It is not really periodic window though, it is just a intermittent periodic behavior in the middle of chaotic behavior, which is called intermittency. It precedes a saddle node bifurcation. This kind of a behavior precedes the occurrence of a periodic window. So, where exactly is it happening? It is happening here inside the chaotic behavior. It is not here, because here it is firmly periodic, period 3. If you go this way, then very close to this you will find that. Another thing that is noticeable is that, notice this bifurcation diagram, the density of points are not the same everywhere. The density is larger here in this part, and the larger here in this part. Okay. Can you see that? So, the density is here, density is larger here, then density is larger there, which means that these parts were visited more often than the other parts. Why did that visit? Because of this phenomenon. If it is there, then it gets locked for some time before it can go away. So, that is the concept of intermittency. Intermittency precedes a periodic window. So, as you can see in the whole bifurcation diagram, there have been a large number of periodic windows, and therefore, that many number of situations where you are likely to observe intermittency. Okay. But the intermittency will be of the same periodicity as the periodic window that is coming. See, in this part you are not here, you are not yet in the periodic window, you are well inside the chaotic behavior, but looking at the intermittent bursts of periodic behavior, you can say that another periodic window is approaching. Okay. So, that is the concept of intermittency. Now, let us understand some other somewhat rarer bifurcations that are observed in one dimensional maps. We have understood two things, they are very, very common, and so you will have to have a very good idea about those two. One, the saddle node bifurcation or tangent bifurcation, and 2 the period doubling bifurcation. But there are also some more which I will now come to. Let us start with the old logistic equation. We had decided that there are 2 fixed points of this. Let us call them x 0 star and x 1 star. X 0 star was at 0 and x 1 star was at 1 minus 1 by mu. Good. The slope of this was dx n plus 1 dx n calculated at x 0 star was mu, and dx n plus 1 dx n calculated at x 1 star is 2 minus. This we have already done. Notice that when you are changing the parameter and it is say passing through 1, the value of 1, let us see what happens. Notice here, so long as mu is less than 1, this value is stable and this value is unstable, and the moment it goes through 1, this value becomes unstable and this value becomes stable, but both of them were existing all through. There is no reason to say that this value does not exist. The only way you would say something does not exist is if you have a quadratic kind of equation with a square root and inside the square root you have a negative number. So, you would say that it is yielding a complex fellow, which cannot happen because I am dealing with a real numbers. So, a real fixed point would mean that its position is given by a real number. If I get a complex number or imaginary number, I know that it does not exist, but here it is not so. Therefore, the fellows exist, but their stability status change. If I now draw the bifurcation diagram, will it not look something like this? I will plot the 0 line somewhere here and let us see what happens, and this is say the value of 1. So, this is x equal to 0. So, the fixed point that is x naught star was existing and was stable up to this point, right. After that it continues to exist at the same point, but becomes unstable. So, let us draw that with red color. Fine. What about the other one? The other one is given by this position. So, at 1 it will have the value 0. So, it will start from here and it will move like this. So, it will move like this, and now it is stable. What is its behavior when the mu was less? It is unstable, but it continues in the same, it is there in the other side also. Okay. So, you would notice that at this point what has happened? There were 2 fixed points which came close to each other, collided, but they did not vanish as it happens with the saddle node bifurcation, but instead they exchange stabilities. While this fellow becomes stable, this fellow become unstable. Earlier this fellow was stable, that was unstable. So, it is like this fellow was unstable, now it has become stable, this fellow was stable, now it has become unstable, they extend stability. Such a bifurcation is called a transcritical bifurcation. It is somewhat rare. Transcritical bifurcations are somewhat rare. You will not easily find that in real physical systems easily, but they do happen. That is why I am teaching, otherwise there will be no reason for me to teach. But the frequency of occurrence of this kind of situation is relatively small. For example, the transcritical bifurcation for this logistic map happened only once, while period doubling happens how many times? Infinite times. No, frequency means it happened for this map only for this parameter value, at no other parameter values. It happened only once, while period doubling happens infinite number of times. Saddle node bifurcation happens infinite number of times, but the transcritical happens only once. So, you will find that somewhat rarely in real physical systems. There is another type, let us try to understand that. That will not be clear from the same map. So, I will introduce any question? I will introduce a different map. Here it is x n plus 1 is equal to 1 plus mu x n minus x n cube. Okay. Now, I will allow you to do this problem now. Can you investigate the stability of this? First, where are the fixed points? In order to find the fixed points, you will have to say that x star is equal to 1 plus mu x star minus x star cube, right. The left hand side is equal to the right hand side. Obviously, there is one fixed point at 0. So, one fixed point at, let us say x 0 star is at 0, and the other fixed point, there are two other fixed points. So, you have x 1 star and x 2 star, let us call them like this, and this is plus root mu and this is so plus minus root mu. Okay. So, there are 3 fixed points. Good. What is the next step? We study their stability, and in order to study their stability, what do? We differentiate this. So, we essentially study d x n plus 1 d x n as evaluated at these 3 points. So, this fellow is 1 plus mu minus thrice x n square, right. So, what will be the condition of stability of this fixed point? What is the condition? Zero, you substitute 0 here, 1 plus mu is less than 1. So, mu is no 1 plus mu should be less than 1, mu should be negative, mu should be negative, negative, but greater than minus 1, okay, minus 2, greater than minus 2. So, we conclude that from
here mu can be negative also.
Yes, we allow that. From mu is equal to minus 2 to mu is equal to 0, x 1 x naught star is stable. Okay. What happens at mu is equal to 0? That means it is going to the positive side, it becomes slope becomes plus 1. Notice this plus 1 thing. So, at mu is equal to 0, this dx n plus 1 dx n at x naught star is plus 1. Okay? And when that happened, this fellow became unstable. Clear? Let us look at the other two fellows. What happens to the other two fellows? So long as, since it is root over mu, so long as mu is negative, these two fellows are not existing, they are not there, right? When, because only after that they become real. The positions are positions would become real only when mu is positive. So, at mu is equal to 0, they start to exist. Good. What is the stability status? Calculate from here and tell me. Root over mu, if you substitute here, okay, he says that if mu lies between 0 and 1, they are stable. Okay. So, we are considering the event that happens at 0 plus, they are stable, and both are stable. Can you notice that? Because both will have the same stability status as given by this. Plus root mu and minus root mu, when substituted here, will make no difference, because x n square, they will have the same stability status. What does it mean? It means that if you plot the bifurcation diagram now, you would notice something like this, that this fellow, I will plot the 0 here. Okay. Minus 2 to 0, this is the 0 position, say. This fixed point was stable. So, at this point, say I reach mu 0 value, and here is the x axis. At this point, what happens? This particular fellow becomes unstable and continues at the position 0. The other one, what happens? Notice that they start to exist and they are having the value root mu. So, it would be one like this, the other like that. Looks like a period doubling bifurcation, but it is not. Why? Because at that point the slope here is not minus 1. In order for a period doubling to occur, it has to have a slope of minus 1. Now, it is plus 1. And what has happened? It is not that a period 2 orbit has started to exist. It is that two individual separate fixed points have started to exist, both period 1 fixed points. Okay. This one is a period 1 fixed point, this one is a separate period 1 fixed point. They have both started to exist and both are now stable. Before this point, they both were not existing at all. Okay. So, notice that if these both are stable fixed points, you might ask where will the actual orbit go? That depends on the initial condition. If the initial condition is here, it will be attracted like this. If the initial condition is here, it will be attracted like that. However, if the initial condition is here, it will be attracted like that, right. So, you will have the orbits going like this. They are both attracting fixed points, they are both stable, but the behavior would be something like this. Is that point clear?
So, but this also we can call period 2 also.
No, it is not a period 2, because if you take the initial condition here, the next iterate will fall here, it will not come here. In that sense, it is not period 2. If it had been period 2, then if you take an initial condition here, in the next iterate it will come here, and then in the next iterate it will come here and go on flipping like this. a period 2 orbit is always a flip orbit, a flipping orbit. It flips from one side of the period 1 behavior to the other. Here it is not, and that is why it has to be given a separate name, and that is pitchfork bifurcation. It looks like a fork. Okay. This bifurcation is also somewhat rare. As I showed that I had to introduce this map in order to illustrate this, because it was not possible to have this bifurcation in the normal logistic map. So, this map is also somewhat rare, this phenomenon is somewhat rare, and it is not difficult to see that it is necessary to have the square term in the derivative, which means a cubic term in the original map. So, only if that has this kind of a structure you observe this bifurcation, else not. So, this is the concept of the pitchfork bifurcation. So, we have come across so far a few different types of bifurcation: 1 period doubling, 2 saddle node, 3 pitchfork, 4 transcritical. Where does it land us? Is it the whole story? By no means, but this is more or less the whole story as far as the first order maps are concerned. That means, we are now considering, yet we are considering only first order maps, and there this is more or less the complete story as far as the local bifurcations are concerned. What do you mean local bifurcations? Here the prime thing in our hand was that we were looking at the fixed point, and we were looking at the stability. What stability? Local stability. Local stability as given by the derivative. Okay. We are looking at only that, and that is why these are called local bifurcations. All these are called local bifurcations. There are also some events that happen not depending on the local behavior, but depending on some global behavior. I will come to that. I will come to that later. For example, the event, did you notice in this bifurcation diagram that here there is something happening? There was a period 3 orbit that went into period 6 and period 12 and so on and so forth, it went on. Here also there is another window, can you notice that? But here there is something happening. Suddenly there were a chaotic orbit with 3 chunks, here, here and here, and suddenly they are all joined, right. The question is, how does that happen? So, these are somewhat global phenomena. These cannot be explained by looking at the local eigenvalues or local slopes, the derivatives. So, we will come to that slowly when time comes. Now, notice a few things. Let us go back to the original one. If you are working in the chaotic zone, that means supposing you have chosen a parameter somewhere here, the behavior is chaotic. From theory, you would know that there must be an infinite number of unstable periodic orbits there. Why? Because if you look at it this way, when this fellow became unstable, the unstable periodic orbit still existed, it continued. What do you mean by the unstable periodic orbit? You have come across once the situation of the unstable point, unstable equilibrium point in the pendulum, right? We did the pendulum equation, and there was an unstable point. What was the unstable point? Like so. Okay. So, slight perturbation, it will go down, all right, but theoretically, mathematically, if it is there, it will remain there, in that sense. In the same sense, these fixed points are unstable, in the sense mathematically, if you place an initial condition there, it will always remain there, but slight perturbation and it will go away. In that sense, they are unstable, which means that inside the chaotic orbit there are really unstable number of such states which if you mathematically place an initial condition on that, it will remain there. Okay, but they cannot remain there because they drift away, they go away from there. How many are there? Now, here this particular one is calculating up to, okay, I'll show just the no. See what I have drawn is, okay, I'll draw some less. I have not shown the chaotic orbit. In the bifurcation diagram, I have only plotted now the stable and unstable periodic orbits. The blue ones are stable and they have been plotted up to the period of 4, and then the unstable periodic orbit. See, at this point the period 4 orbit starts to exist and that continue. At this point the period 8 orbit starts to exist and that continues, and so on and so forth. Oh, period 6 orbit. No, this is period 3 orbit that continues. So, as it goes on, this keep on multiplying. If I calculate up to a period of 6, you see more. Okay. So, as it goes into the chaotic orbit, there are all those red lines, means there are all those unstable periodic orbits. Let us calculate it for some more, the period 10 orbit up to. See, already it is becoming so cluttered that it is not difficult to see that as it goes more and more into chaotic zone, there are more and more unstable periodic orbits available in the system. Each one you may visualize as a pendulum standing on your upside down. The interesting thing is that if the pendulum is standing upside down, it will normally fall, but you might also hold a finger under that, and with some small perturbations you might keep it vertical, right? You have all done that with sticks, right? All these are such things which can be stabilized that way. So, a chaotic orbit then allows far more freedom, because a lots of unstable but periodic behaviors are now available, which were not available if the system is stable. Because the system is chaotic, a lot of unstable periodic behaviors are now available, which can be stabilized the way you balance a stick. We will come to this issue later, how to stabilize them and what kind of work we can do with that, but such flexibility we have in dealing with chaotic systems, that you should understand. Clear? If there is any question, I can answer, so long as what I have taught, else I will go to I have to go to the second order maps also now. Next.
So, in the end, what did you say, like there is some this is the flexibility behind?
Yeah, I said that there is a lot of flexibility in the sense that if the system, suppose a system is a linear system, a linear system means its behavior are exactly given by the eigenvalues and that is it, you can do nothing about it. If you want to do something, change the eigenvalues. That is how the whole of control theory works. You put some feedback, and that feedback essentially changes the whole system's eigenvalues, and that is how it works. If it is a nonlinear system, then you have more flexibility in the sense that if something becomes unstable, it does not really immediately mean that the system will collapse, because some other orbit may become stable. For example, here you have seen that when the period 1 orbit becomes unstable, the period 2 orbit becomes stable. So, it does not collapse. Now, suppose in addition to I saying that it is not only nonlinear, but also I have chosen a parameter range in which the system is really chaotic. there are some applications where you might want chaos, for example, spreading the spectrum and stuff like that. I will come to that later. But even if suppose you want to behave in a regular periodic way, then the question comes, which periodic? If it is linear, you do not have the option, there is only one thing available to you. If it is chaotic, you have infinity of options, you can stabilize any of them. So, you have a lot more flexibility in your hand. In that sense, I said that dealing with a chaotic system is a lot more flexible. That is why you might possibly know that the wherever you want a lot of flexibility, you want to design the system in a sort of unstable way. For example, the big airliners, they have a control system, right? They will have a autopilot, where the pilot goes up and then he lifts it to the autopilot. The autopilot does it. It's a nice control system that has everything very well set, but you cannot do that for fighter pilots. For the fighter aircraft, you cannot do that. It has to have very large maneuverability and very fast response, and for that all fighter planes are therefore made open loop unstable, and the loop is closed by the pilot holding the joystick. Unless it is unstable, you cannot really have that flexibility. So, that tells you something, that in order to have flexibility, you also want some kind of a instability, and this is this instability. You have at every point it is unstable, all right, but with slight perturbation you can stabilize it. Okay. So far we have mainly been talking in terms of one dimensional maths, where you have the expression x n plus 1 is equal to some function of x n. In general, you would not expect this kind of things. This is too simple, but still we went into it for two reasons. First, it gives a nice visualizable way of understanding dynamics, because you can draw the graph of the map, you can draw those cobweb diagrams, thereby understand the behavior of orbits. But this really is too much simplification, you might say. Not quite, because in many systems it has been found that even though the actual system appears to be far higher dimensional, for example, there is no reason to believe that the dripping faucet experiment will lead to a one dimensional system. It is not one dimensional, obviously. If you really want to model it, it will lead to a very high dimensional system. Similarly, there are many systems in nature as well as in engineering, which if you write down the equations accurately, they are very high dimensional, very complicated things. But when you actually observe their behavior and plot x n versus x n plus 1, if you get a nice looking curve, what will be the conclusion? That even if the actual system may be very high dimensional, but the dynamics can be modeled by a low dimensional model. For example, that we have seen that which one I am forgetting, that was probably, let me just get into that again, Poincare sections and this one. This one was the Poincare section for the Rosler equation. I want to plot a larger number of points. So, see here it is actually 3 dimensional system. Place a Poincare section, you are expecting a 2D map to come up, yet when you actually plot it, you find that it is on a nice curve, which tells you that even if the actual system is 2D in discrete time, it can effectively be modeled by a one dimensional map. So, in that sense the one dimensional map study is fruitful. Okay. You have also seen that in case of the dripping faucet experiment, you yielded a behavior something like this. I have not brought that book today, but it was more or less like that, x n plus 1 x n versus x n plus 1. Only it had a little bit of like this. Remember yesterday I showed this little bit will tell you that in only that sense it is not exactly one dimensional, but if you can ignore that part, if you can approximate it by this, then it is more or less one dimensional behavior. Again in that sense the study of one dimensional maps are fruitful, but in the main the study of one dimensional maps helps us in understanding these bifurcations in very concrete terms. Mathematically most of these can be worked out by hand, but then we have to take the next step, we have to go to the second order systems. So, we now need to study equations of this form x n plus 1 is equal to function 1 x n y n and y n plus 1 is equal to another function of all right. In this case, how will we proceed? We will proceed by the same way, though now we are no longer able to plot the graph of the map, because we are constrained in our plotting to the 2D thing, and here the space itself is 2D, and therefore, I cannot plot x n plus 1 or y n plus 1. So, we cannot plot. We are no longer have the option of plotting the 45-degree line and finding the intersection, we cannot do that. Still, can we find the fixed point? Of course, we can. How will we find? Simply put x n star in the left hand side and y n star in the right hand side, and then equate them. You will get a pair of algebraic equations. Solve them. You will get the locations of the equilibria or the fixed points. How will you study the stability of the fixed points? Yes, we need then some equivalent of the derivative, in 2D. Imagine you have the x and y, x n and y n, and suppose you have plotted the x n plus 1 here. It is not difficult to imagine that you can plot this way, right. So, you have got this horizontal plane x and y n, and you get the. So, you have some kind of a surface kind of thing, and you are trying to find out the local linear behavior. Say at this point I want to locally linearize. In case of a 1D graph x n versus x n plus 1, a graph like this and this point, and you take the derivative, the derivative was the local linearization. You similarly you want to take the local linearization here. Now, this local linearization here, where you are taking both x n plus 1 as well as y n plus 1, is given by the Jacobian matrix. Probably you have learned that in the mathematics classes. That is given by the Jacobian matrix, and the Jacobian matrix is expressed as all right. So, here also we will take the same route, we will look at the fixed point and look at the local linear neighborhood, but the behavior in the neighborhood of that fixed point will be given by the Jacobian matrix, and we will expand on this idea in the next class. Okay. That is all for today.